Morning, everybody. Thanks for the introduction, Artem. So today we have our tutorial session. Um, our first tutorial is Libfabric Communication Library. Uh, Libfabric supports multiple communication semantics, is fabric and hardware implementation agnostic, and leverages and expands existing RDMA open source community. Libfabric is designed to minimize the impedance mismatch between applications, including middleware such as MPI, SHMEM, CCL, etc. This tutorial focuses on new features like the link provider, bridging different providers, and the usage of this new link provider. Our speakers will also focus on updates with the Ultra Ethernet and Libfabric. Our speakers today for this first session are Rajalaxmi Angadi, who is an engineer, leader, manager at Intel Corporation with 20 years experience in HPC AI communication software and storage technology. She co-chairs the Women at Intel Network, a senior women community fostering growth for women in tech. She holds a patent and has spoken at multiple conferences. And Alexia Ingerson, who is a software developer at Intel working as a maintainer of Libfabric. Her focus areas include shared memory and GPU transports. Please help me in welcoming our tutorial speakers. We're going to have, I think this is an hour and a half, and we'll have a short transition afterwards. So if you guys want to take it away.
Thanks so much. Let me just get Sharon.
Thank you.
All right, Raj, all you.
Still cannot see the
Oh,
screen.
you can't see my screen?
Yeah.
Oh, no. Try again. Sorry.
It's coming.
Okay, now all you.
Yes. Yeah. Yeah. So, hello, good morning, good afternoon, and good evening. Welcome to Hot Interconnect 2025. This is Rajalaxmi, along with Alexia, are here to present yet another tutorial for Libfabric. So let's see what we have in the box today. So we will cover a quick overview of Libfabric, and then we will recap from our previous sessions to set the stage. We will be covering link provider in detail, and we'll also touch upon Ultra Ethernet Libfabric mapping. So without a delay, let's dive in. So let's start with an overview. Over the period of time, hardware has evolved, and it is still evolving in all areas like compute, network, memory, and storage. So the type of applications and the use cases are also rapidly growing. With the advancements in GPT, for example, we are dealing with trillions of parameters, which means a lot of computing capability is required. And we know that we cannot fit these models or compute them on a single machine or a server. So we need a lot of compute engines that needs to be connected via some sort of fabric so that we can operate on this large amount of data and produce results. A lot of communication is involved. So Fabric interconnects is our focus here. So what are the developers dealing with when they want to program to these type of fabrics? So we have fabric solutions with Ethernet, InfiniBand. They are provided by various vendors like Intel, NVIDIA, Cray, Cisco, etc. The developers are overwhelmed with so many variety of hardwares to program for, and also at the same time, cater to the needs of the applications. There are so many interconnects, so many APIs from each one of them. And there are also questions on how do I adopt with a new technology or whenever a new fabric is introduced. Hardware developers want to differentiate the hardware with variety of cool features that they bring in. But at the same time, the software developers or the application developers, they like uniformity. So is there a way out or is there an easy way out? So this begs for a need to have a standard way for handling different fabric hardware. So at the bottom, we see here we have different type of fabrics, and there are different vendors that are providing these different type of fabrics. We can see that there are fabric hardwares from different vendors, like again, like I mentioned, Intel, Cisco, Cray, Mellanox, NVIDIA. They have their own kernel drivers and user space interfaces. On the top, we have applications and middleware libraries. Now, if a developer wants to program for, say, Ethernet NIC, we go with the socket APIs. Similarly, if one wants to program for InfiniBand, then we go through the RDMA subsystem or through the IBverbs APIs. And similarly, if they want to program for a shared memory, then they require its own APIs to be used. Or like if they want to program for any other type of device, then there are like specific APIs for those. So this is inefficient and it is expensive to maintain such code as well. And it's not also portable. So this is where Libfabric comes to rescue. It provides a common interface to a variety of hardware and its features. It exposes the features from those underlying hardware in a uniform way to the middleware libraries. And it does it through these various providers that are shown there. Like we have TCP provider, VERBs providers, the SHMEM provider, etc. So, for example, the TCP provider like bridges to any socket hardware. The VERBs provider like enables to run on any VERBs hardware like InfiniBand, iVarp, etc. And thereby, the developers can just use that common interface APIs from Libfabric to code to these different fabrics. So code is also portable. It is also easy to maintain. An example that demonstrated this efficiency was going from MPitch to MPitch CH4 version with the instruction count for MPI ports approximately decreased from 1300 to just 215. So this is the power of a common abstraction that is provided by Libfabric. So let's look into the features of Libfabric. So in this diagram, we can see that the Libfabric is sandwiched between the middleware on the top and the rest of the lower layers. So on the top side of towards the middleware, it defines a standard common communication APIs for HPC and now these AI applications or the middleware libraries. And it does it by mapping those to the lower layer fabric services to the interfaces that are exposed to the applications, and it aligns more on the application side as well. So this provides the tight semantic mapping between the various features from the hardware and the APIs that are exposed to the applications on the top. So it is designed for performance and scalability. And how does it do that? So it provides flexibility by supporting various underlying transports and allowing applications to choose the best suited transport for their needs without having to program for that specific fabric. And another feature is like optimized path selection. This allows selecting the best transport based on the various performance characteristics that are desired, such as latency or bandwidth. The other features that contribute to the performance are like zero copy transfers, efficient memory registration, that will overall reduce the amount of system calls, lazy registrations for on-demand or dynamic registration of the memory, or efficient memory pooling, or it could be endpoint abstraction and flow control techniques. So all of these things make it performant and also scalable. So APIs are simplified, yet they provide fine-grained controls. The key components of OFI are its application interfaces, the provider libraries, the kernel services, and the test applications. And Libfabric is supported on various operating systems and distros. So the latest version of Libfabric is 2.2 that was released recently. So let's zoom into the Libfabric itself and see what are its components. So the major components of the Libfabric are shown in the blue box at the center. Just like we have seen the stack diagram in the previous slides, the top is the application middleware, and at the bottom we have squeezed everything related to the hardware and its kernel software into those gray boxes there. There are different kind of APIs that are available or exposed to the applications or middleware. So we have divides it into the 4 groups of APIs here. The first one is control APIs, then the communication APIs, then we have completion, and then we have data transfer APIs. So these control APIs are those that will work with the control like discovery, like for example, FI get info, FI control. These are for controlling the aspects of Fabric, such as querying the status, configuring parameters, etc. Then we have communications. This is another big set of services that help with the connection management, like setting up endpoints, domains, handling address vectors, um, and things like that. So data transfer is also a major chunk here, and it deals with different type of data transfers like messages, remote memory access, tagged messages, automix, and collectives. So automix transfer data and also do some operation on it. Operations like sum, min, max, etc. It will be like read, modify, write. So not all Fabric providers support atomic operations. The availability of atomic operations will depend on the features that are provided by the underlying hardware as well. Then we also have collective operations. It is a group of, it's a group communication exchange. This involves like multiple peer exchanging the data with other peers that are participating in that one collective call. Then we have a completion set of APIs. So these are used to signal the completion of various events. They signal about completion of events and counters, and they also signal on the wait events as well. And for example, whenever writes are posted, the completion queue is updated. Then at the bottom of the Libfabric chunk itself, we have the providers. Each NIC hardware has its provider. So these are the specific implementations that enable communication over various transport protocols and hardware. So each provider is designed to support different features like performance, characteristics, and different use cases that they bring out. They can also be tuned for like latency, bandwidth, scalability, etc. And applications can select a particular provider based on specific performance requirements that they have for their applications. So some providers offer reliable communication, ensuring the message delivery, while other providers may offer like faster and unreliable connections. So certain providers support atomic operations for synchronization and coordination, while some providers may implement or like offload the collective communication operations. So which are key for our parallel processing these days. So we see that there are different providers like TCP, which supports sockets, Verbs, which is for like InfiniBand type of hardware, and there is shared memory provider. And we can also see that there is UEC's Ultra Ethernet transport as well, which will eventually be the provider under Libfabric. So these are the types of providers, and each vendor can have their own provider of this type. For example, if there are like multiple vendors offering UET type of hardware, then there will be like multiple of those UET providers. Next, we see in the center, we see that there are utility providers. These are specialized providers that offer additional functionality and services that are beyond the standard communication capabilities. So these providers are designed to enhance the overall performance and the usability of Libfabric framework itself. So we have RxM provider that supports RDM type of endpoints that are emulated over message type of an underlying core provider. So for example, the message type provider could be like aligning with the TCP provider. So, and it can handle like connection multiplexing, it is suitable for applications that are requiring message passing with reliability and ordering. And similarly, we have other providers as well that add some additional capabilities. So we also have the link provider, which we will be discussing in great detail later today. This will help bridge between two providers, and we will be covering that later. So another one is the profile hook provider. This is used for us to be able to profile um, various features of Libfabric itself and the features that are exposed by the provider itself. So let's revisit what we have covered before we talk about any new stuff.
Yeah, so first let's start with a simple recap of our previous presentations. We've presented for, I think, the last 3 years at this conference, and there's been a lot of information that we've shared. So I'm just going to start off by going over some of those key pieces and then condense them down to just start us off with a base level. So first of all, Libfabric is available in major distros like Raj said, but we always recommend building from source to get those latest updates. Sometimes it takes a while to get the latest update into the distro, and we're always constantly updating and releasing. So it's always best to just get the latest fixes from upstream. Our release schedule is about quarterly, and all of these new releases are available on GitHub. So you can just grab the latest and greatest from there, or a specific version if you need it. We just released 2.2.0 in July. We also have a new release coming up in September. That'll be our Q3 release, which will be 2.3.0. Sometimes we do minor bug fix releases, but we do those just as needed when issues arise. So for the most part, they're just quarterly. Libfabric uses auto tools for building. So if you're cloning from the repo, then you have to call AutoGen first, like I say here. But if you're just grabbing it from the tarball from the release, you can just go straight to the configure and then just pass in your install prefix. There's a lot of different options here that you can specify in the configure. For the most part, Libfabric will just pick up the default libraries that are available on your system, but you can always modify your install as needed depending on your cluster requirements or limitations. We also have a subdirectory that's in the repo. It's included in there. It's also available as a separate tarball in the release page. It's called FabTest, which is our testing and validation suite, which also could be useful. You also use AutoGen and configure for these tests, passing in that prefix for installation, as well as your Libfabric install directory in case your Libfabric is installed in a non-default location, but otherwise I'll just look for the system install. Okay, so here's a general look at the OFI architecture in the resources. Not all of these are required, just an overview. Some of them depend on which features you decide to use or what providers you plan on supporting. But at the top, the first thing is your fabric. The fabric is the first resource that you will be creating, and you can't do anything else without a fabric because this is just the gateway to all of your other resources. So the fabric represents the collection of hardware and software resources that all access the single physical or virtual network. So all the network ports on a system that can all communicate with each other through their attached networks, those are all in the same fabric. All of the other Libfabric resources are all allocated within the space of that fabric or network. Passive endpoints are allocated directly under the fabric. They're only required when using a connected oriented protocol. So the passive endpoint is where you're going to be listening for incoming connection requests and then accept those connection requests. And then the events associated with that connection management, like those incoming connection requests to the passive endpoint, those are going to be reported on an event queue, which is also directly allocated under the fabric. Then under the fabric, there's also the domain, and that defines the boundary for all your fabric resources. So that can include memory regions that are registered for data transfers, address vectors, which are used for reliable and unreliable datagram protocols for address mapping, and then also completion structures such as queues and counters. And then the active endpoint is also allocated under the domain, and this is going to be your gateway to communication. So all your data transfers are going to be initiated on the endpoint itself, and that endpoint may be connected or unconnected. So When you're choosing what type of endpoint to use, there's a few different considerations, really two. The first is whether your data is reliable or unreliable. So a reliable connection would mean that all the data sent from one endpoint is guaranteed to arrive at its destination, which is in contrast to an unreliable connection where some of the packets might get dropped due to congestion or lack of resources, your hardware. So from a socket's point of view, you can think of this as TCP versus UDP. The second consideration, excuse me, is whether your endpoint is connected or unconnected. So that is whether you have a one-to-one relationship between a sending endpoint and then a receiving endpoint, which needs to be managed with your typical listen, connect, accept flow. So again, you can think of this as TCP versus UDP. So with a regular TCP socket, you have to manage your end-to-end connection and listen and accept. And then that single socket, once established, can only send to one other address, and that data is guaranteed to arrive. A UDP socket, on the other hand, gives you the luxury of only having to manage a single endpoint and not worry about those connections to send, and then you can send to multiple peers. But the drawback is that your data may or may not arrive depending on your network status. So OFI has equivalent types for these typical use cases. We call them EP message, which is your connected and reliable protocol, so TCP-like, and EP datagram, which is unconnected and unreliable, so more like UDP. The connected-oriented protocol uses a similar listen, connect, accept API like sockets, while the unconnected protocol uses that address vector to map native addresses to an OFI FI adder, which is just basically an index array to access in an array. But what if you wanted to be able to use a single endpoint where you didn't have to manage all those connections and also your data is guaranteed to arrive? So it's kind of that sweet spot in the upper right-hand corner there where you get an unconnected one-to-all endpoint, but your data transmissions are also reliable. So OFI blends the benefits of both of those use cases into a single type that we call EP RDM. The RDM here stands for reliable datagram. So this gives the application the illusion of a single reliable endpoint for transmission, but actually underneath it's using a connected, oriented, or unreliable protocol underneath, or the unreliable protocol underneath. So while the RDM flow is much easier to use from the application's point of view, most hardware interfaces are connected oriented or connection oriented. So OFI has what we call utility providers that act as built-in abstraction layers to implement an endpoint that's usable through an RDM interface, but it's actually using that message or datagram flow underneath. So one of these commonly used utility providers is RXM, which I'm going to go over as an example. And RXM stands for RDM over message. So RX, which is over message. A lot of people don't know that. So it exposes an RDM endpoint for the application, but actually underneath it's using a message endpoint. So RXM here in dark blue manages the relationship between a single RDM endpoint in light blue that it exposes as a gateway for the app, but then multiple point-to-point message connections for each peer that it's talking to. So those are the ones in purple. So in this case, RXM is actually managing all the connections and the multiplexing for the application, and is maybe using the perhaps limited functionality of the core message provider of just its regular message and maybe RMA capabilities to expose a single, easily manageable endpoint to the application. And that endpoint is going to have full message tagged RMA and atomic functionality. So the target use case for the RXM utility provider is basically any hardware with a reliable connected semantic, such as verbs and TCP. Obviously, if we're talking about hundreds of nodes in our usual landscape, we don't want RXM to assume that we're going to be talking to everybody. So one of the things that RXM does to reduce the number of active connections is it creates connections on demand just as needed. So here's an example of what that on-demand connection management would look like to illustrate how RXM might use a message endpoint underneath without the application's knowledge. Again, you have RXM space in the blue here, and on initialization, it creates a passive endpoint to listen for incoming endpoints or incoming connections. The app then calls AV insert to add the peers that it's communicating with, and then we'll bind that AV to the RDM endpoint. But at this point, we still haven't created any connections. It's not until that first send that RxM knows to create a connection with that peer. So at that point, it will create the message endpoint for the data transfers, and then it'll call connect. The peer will accept that connection request, which will allow the send to fully go through on that newly created connection. So at this point, we only have one connection, and it's not until a second send for a second peer in that the whole process that it will all get triggered again. And that will create another connection to that second peer. So if your whole application involves thousands of ranks communicating with each other, RxM is only going to initialize those connections that are required in your communication pattern, and it will do it without your knowledge, so you don't have to do anything to manage them. Once you have your endpoint all set up, you can use a variety of APIs, like Raj mentioned, to fine-tune the communication in your application. I won't go into in depth on all of these APIs, but they tend to fall into two categories. Those are send and receive and remote memory access, or RMA. So a send receive API is a two-sided call. So one side has to specify which buffer to send, and the other one will specify where to receive that message into. So it'll post a send and then receive it. In contrast, an RMA call is only one-sided, so the sender will provide both the source and remote target memory location. And those operations require no response or matching from the target side. There are two types of send and receive calls: regular message calls and tagged calls, which are pretty much the same, except that tagged calls allow for posting messages with a tag. So that can be used to match receives to specific buffers, basically allowing for grouping of messages. There's also two types of RMA calls: regular RMA, which issue a direct read or write into remote memory locations, and then atomic operations, which will do a write or read into a remote location, but also will perform an atomic memory operation, like maybe a sum or a compare swap along with the data transfer. Not all hardware supports the full set of capabilities that we have available natively, but providers often add abstractions on top of the hardware implementation to provide that full set of capabilities. So that's one of the advantages that I was mentioning with RxM, that verbs and TCP don't natively support all those capabilities. So RxM not only removes the connection management portion, but also adds that full message tagged RMA and atomic capability set, which is why we see more applications use verbs with RxM than raw verbs. There's another set of data transfer APIs which doesn't fit into either of these categories, but Raj is going to discuss those specifically in a little bit here.
Thank you. So now that we have seen like different providers, utility providers, and different type of data transfers, we will quickly review the examples with message, RDM, tag messages, and collectives, and we will also review profiling. So let's see the examples. So imagine you have an Ethernet interface and you want to program for either a simple client server or for a send receive, or you want to program for a complex distributed system to solve complex problems. Imagine if you didn't had any abstractions there. So we would traditionally program using standard sockets. So there is a client that is trying to connect to the server and wants to send a message. So the server opens the socket descriptor, binds it with the address and port number, sits there listening in the passive mode for any incoming connection. And when the client sends the connect to the right address or to the appropriate address, the connection is established and the data send and receive follows. So this example on the left side shows that connection-oriented setup with reliable messaging, and it's using TCP provider. So imagine if one has to, if they have a different fabric and there are like different interfaces, then they will have to rewrite to the different set of APIs for different type of hardware. It would be inefficient. So on the right, we show an equivalent example with Libfabric APIs. So we use FI, EP, message endpoint, which is connection-oriented connection for reliable transfers. And it is just doing the similar thing for like the left side program. So we can use this with different providers like TCP verbs, and it can run on the hardwares that are supported by these providers. And it uses FI send and receive for the data transfers. So we see that the same set of program can be done with the Libfabric APIs, and Libfabric just provides those just common interfaces without having the developers to change for different set of hardware. So now let's look into the RDM type of endpoint. So RDM, like Alexia mentioned, is reliable datagram message. It provides a reliability over connectionless connection. And the data service flows with the control that maintains the message boundaries. Libfabric provides this reliable communication mechanism that combines the benefit of low latency data transfers underneath, and it also assures the message reliability. So, and again, here we are doing the data transfers with FI send and receive. So like we saw the example in the previous slide, this example also looks similar. First, it opens the Fabric resources and creates those resources using like FI Fabric domain, and then RDM endpoint is created. Notice that we have specified the endpoint to be FI EP RDM here. We can use this with different providers like, again, TCP or verbs via utility provider, and it can run on the hardware that are supported by these providers. So FI send and FI receive are again used to transfer the data here. So now let's look into another type of data transfer. So we I think I forgot to mention that we have those three type of endpoints that Alexia mentioned, like FIEP message, FIEP RDM, FIEP datagram. And there are different types of data transfers like message, tag message, RMA, atomic, and collectives that we covered in previous slides as well. So let's look into the tagged example. So this is an example showing the tagged messages. Again, we are using RDM endpoint here, which provides reliability. So where do we need tagged messages? So if we have like multiple operations or multiple collectives that are happening at the same time, then tagging the messages will be helpful to identify the messages that we are interested in. And we can also have we can mask the tags that will provide us the complex tag matching schemes. Ordering can also be achieved with the tagging as well. So if we are like expecting the messages to be received in a certain order, then we can wait for those message with those particular tags. For example, if we are waiting for a message with tag 1, we can match that message and we can receive that. So in this example, the flow is similar like what we had discussed in the previous slides, like it will create various Fabric resources, binds them, and inserts addresses in the address vector. And then followed by we call the data transfer APIs like tsend and treceive here instead of the plain FI send and receive. So tsend and treceives are for the tagged messages. So next, let's look into an RMA example snapshot. So RMA is remote memory access. It's a powerful feature of RDMA that allows one node to directly read from or write to the memory of another node without involving the CPU. This capability is particularly beneficial in the high performance computing and now AI as well, and also for data intensive applications, as it helps reduce the latency significantly and there's no CPU overhead. Before performing RMA operations, the memory regions that are involved for the data transfers, they must be registered with the provider. So this registration allows the hardware to access the memory directly, ensuring the efficient data transfers. So we can see in this example snapshot that the memory registration is done with different OFI APIs like FIMR reg, FIMR disk, and FIMR keys, and such APIs. So RMA supports several type of data transfer operations, including reads, writes, and atomics. So reads allow a source node to read the data from a specified memory location on the target node, whereas write enables a source node to write data directly to a specified memory location on the target side of the node. And we have atomics. They support read, modify, and write operation, wherein it'll modify the data by doing some operation like sum, average, or like increment, and then write it back. RMA operations can be synchronized using various mechanisms, and this is where the completion APIs will come into picture. So completion queues or event notifications are used to indicate the completion of a particular event. For example, to ensure that data transfers are completed successfully, we can wait on those particular write event or the read event. I mean, we basically read that event to ensure that the transfer is completed. So different providers also support RMA operations with RDM endpoint. And in this example, we see that we have used FI-EP RDM, that's the RDM endpoint, and we are doing the RMA operation by specifying the capability FI RMA with the write and reads data transfer calls. So now let's look into the collectives. So a collective operation is a group exchange, group communication exchange, and it involves multiple peers that are exchanging data with the other peers, which are participating in that collective call or the collective group. So collective operations can be thought of as a coordinated atomic operations between a different set of peers. So this example is a simple reduce example with sum operator that we want to do. Basically, we want to find the sum of the elements. So the root rank wants to find the sum of the elements in the array at the appropriate indices from all the other ranks or processes here. So there are various algorithms to do so. Here is a simple ring one, and it's not the efficient one, I know, but just to demonstrate how there are different processes involved in the communication and how they have to like exchange the data to solve that one problem. So the rank one sends its array to the rank two. The data is then operated on, and then it passes it to the next rank, and similarly it gets operated on, and then we do again like use the APIs like tsend to transfer the data, and then ultimately the root rank will receive the sum of the elements at the corresponding indices. There are again, like I said, there are much better algorithms to do these kind of things, but here we see that we are doing the sense there is a connection establishment, there is sense that are happening between the nodes. So let us look into the Libfabric collective APIs itself. So this is the flow showing how collective APIs are used. There are basically 3 steps when dealing with collectives. So one, we have to identify collective membership. The second, we have to set up the communication group. And third, we have it will be about the invoking collectives itself. So when it comes to identifying collective membership, we have to find which processes are part of this collective group. Like in the previous example, we saw there were 4 processes. So this is a local operation. With the regular connection or with the regular simple programs, we normally have address vectors representing who are part of the communication, right? The peer universe is what we call. The endpoint, which is the IP address plus the port information, that is mapped into the address vector tables. as the fabric addresses. But with collectives, we have to extend that address vectors to the address vector set, which is a collection of peers in a collective group. So there are FI underscore T type indices of the peers that are part of this collective group. So address vector set maps to the multicast address. So it's a new FI address value. So when this address is passed to the data transfers, then those data transfers are done to all of those peers that are part of that group. So if we, for example, if we are doing a broadcast, then if we send that broadcast message to that multicast address that's from the AV set, then it is get sent to all of the peers that are part of that group. Now this is identifying the membership. So next we'll see the setting up of the communication group, which is like join collective. To set up a collective, we call like join collective. Then AV set will have its own multicast address, which will be used to make the join based on this AV set. And we will have the set of endpoints in this new multicast group. So how can the setting up of communication happen? It can be done in two ways. One is the OFI managed, and the second one is application managed. With OFI managed, the application calls join collective, which is implemented by the provider underneath. And the provider will then talk with the peers and then reserves those resources and sets up those communication groups. So once the join call completes, we will get the address and that can be used for all the further communications. Now, in the application managed, the communication group is established out of band, and it's either by the application or the middleware library. So the resources are already reserved there, and the members of that communication group are already identified. So it is just conveyed to the Libfabric layer. So when a join collective happens, we get that one multicast address. It can either join an existing collective group, or it will create a new group, multicast group, if there is not a previously created address. So if there is no, I mean, if it's creating for the first time, then we do like FI ADDR unavailable flag that will help us specify that there isn't one. So join call is asynchronous, and it's also a network operation. So the application will get blocked until that join is completed. So we can see here that we are waiting on the event queue as read here. So that will say that we'll wait for all the join to happen. So all of the peers that are part of that collective group will join. Now the third part was invoking the collective itself. So FI all reduce is a call that's shown in this example, but in the previous slide we showed just the reduce one. So the all reduce is the actual collective operations. So there are different type of collective operations like all to all gather, all reduce, and reduce scatter, and things like that. So now that we have seen like different data transfers and different endpoints, and the how those endpoints are supported by different providers underneath. We have not covered Automix and Datagram given the time we have. So we will just talk about the profiling that we had covered before. So let's revisit that one. So this is another thing that we had covered. For all the examples, you can also like refer to our previous tutorials. You can have details there as well. So profiling is used to help us debug and understand the communication characteristics. So it can help us understand like how the communication APIs are used in an application middleware, and it will also help us find the like performance differences between like different network interfaces or using different network communication protocols. And we can also gain insights into how a particular provider is implemented, and also understand like what are its limits, and how can we like optimize the resource utilization over there. It can also provide aggregate statistics in the Libfabric, and this profiling tool is also very lightweight. So there are two parts to the profiling. One is the profile hook, and this will help us understand. And the second one is the fabric profile interface. We'll touch on that a little later. So profile hook, this will help us understand the communication APIs. So Libfabric has got, it kind of interfaces on the north with the middlewares and applications, right? So it will help us understand like how these APIs are being used with when they call into Libfabric. So it intercepts at the Libfabric's external interface to the upper layers, and the goal is to understand like how the communication APIs are actually used. Like what is the like if a given application, like what are the data sizes that they are normally calling these applications with, or like how many times are these being called, right? So it is built by using Libfabric's hooking mechanism, and it hooks like send and receive calls, memory region registration calls, completion calls, and things like that. So for example, FIT send, FIT receive, and completion queue read, etc., like our profile. In that small snapshot on this slide, wherein it shows some numbers, you can like zoom, and I know it's not very clearly visible, but it is basically showing the different API calls that were made from the application. And it is also showing an histogram of message data sizes that were being operated on. So for example, FIT send has been called with different message sizes there. And we will also see like how many times it has been called and what's the percentage of it. So that is what profile hook will provide us, and it will help us like to analyze. Okay, given an HPC application or an AI application, okay, these are the type of calls that are being made, and they are the data sizes that are being used by these calls are so and so. And the next part is the FPI, which is a fabric profile interface. This is used to profile the providers. So it is a part of the provider implementation as an external extension to the provider, so that we can debug and profile the capabilities of the provider. So it allows the provider to expose its internal info. Of course, the provider will have to decide like what information it wants to expose. It will enable the applications to discover and query these profiling capabilities. And how it does, like first one is like, what do we want to profile? Like what do we, like these are the variables that the providers can make available as a shared information. So this is the what part. So what exactly we want to profile? For example, we want to profile on the unexpected message count. Okay. And we want to see like what is happening with unexpected message count. And the next part is like the events. So it will tell like when do we want to profile. So these provide information about the events that influence those variables. Like and it is the part, it is the when part that we want to monitor those variables. For example, if we want to monitor like unexpected message count, and we want to monitor it only when unexpected message receive event has happened. So that's the when part. And then the third part is the APIs. These are the APIs that will help us do these things. Like, how do we like, monitor these, and how do we trace these? So it's the how part. So how are these variables profiled? So these are set of APIs that will help us profile. So there are different type of APIs that is also specified on the screen. So the discovery APIs are used for finding out the variables. So it will help us find out which variables are exposed by the providers that are available for profiling. And register and deregister APIs are used for setting those callback events to specify like, okay, these are the events when we want to like, monitor or like, get the counters when these particular events have happened. Then there are querying APIs to actually read those counters. So this is mentioned on the slide. I mean, those set of APIs and there are also like start and read APIs that will tell us like, when do you want to start the profiling and when do you want to end the profiling. So this is about the profiling. I would like to hand it over to Alexia to cover the link provider next.
Thanks, Raj. So yeah, one of the reoccurring problems that we've started seeing in these modern applications centers around the idea of shared memory and optimized intranode offload. With these modern systems, they're increasing their core count dramatically. It's really important that we have an accessible intranode solution for our OFI users, because what ends up happening is that every application has to write their own shared memory implementation to offload communication from the network. Which is all fine, but it requires an increase in development time for application developers, and then also adds to maintenance costs for them. So because of this, we added a shared memory provider years ago to provide apps with a common OFI coded solution to reduce development and maintenance costs for them. But unfortunately, no one was using it because it required changes from the applications to allocate and manage two different OFI providers, one of them for core remote communication, and then also another one for shared memory, the shared memory solution. So the app would have to manage all the resources allocated for each of those providers. So that means two domains, two memory regions for each single buffer, two address vectors, and then each one would have different addressing schemes for that matter, two completion queues, and then it would have to post receive separately to each provider, make sure not to starve one provider of the receives. It gets really messy and complicated, to say the least. So to fix this, we developed a set of APIs that we call the peer API, which allow multiple providers to share resources together, so to be used as peers. So basically, one provider could own a resource and then import it into another provider for it to use directly. These APIs are not intended for applications to use, but rather for providers to use internally to communicate with instances of other providers. And as an extension of that, we also started developing a new provider that we call the LNX provider, or link provider, whose goal is to link two or more providers together using that peer API, and then direct communication to the best providers for the job. So what the peer API and link provider aim to do is to allow applications to leverage the shared memory provider without having to change anything in their application. So all it has to do is just basically switch which provider that it's using, and it can have built-in optimized intranode communication without any headache for the app. So while this doesn't require any app changes, it's still important for everybody to know what's going on underneath. So we wanted to cover the topic today to show what we're doing in OFI to make all this happen, which can help people know whether it could be useful for their application. So let's dive right in. As I mentioned, a big target for this is for using a remote provider and the shared memory provider to optimize intranode communication. But another use case that we're looking at is to use it as a tool for multi-railing across different NICs if you have them available. So essentially, you can link together NIC 1 and NIC 2 for your remote communication, and then use shared memory for all your local communication. Right now, I'm just going to be focusing on the shared memory use case because that's our primary case, but that is an extension that we're looking at and actually something that works preliminarily right now. So for that case, specifically, we're going to be exposing one endpoint to the application, again, requiring no changes on the app side, but underneath, we're actually using two providers, one of them for external internode communication, and then one for internal intranode communication. In order to do this, we will have to share a few different provider resources. The first one is we'll have to be able to write to the same completion queue or counter, so we don't have to transfer completions from one queue to the other. The second one is we also have to get receive buffers from the same receive context, or SRX, which you might see, and that stands for shared receive context, SRX. In OFI, we have something called directed receive, which allows us to post receives for a specific peer. So That use case is really easy to handle with two peers, since you could pass through the receive buffer directly to the provider handling the communication for that peer. But we get into really tricky territory if we start trying to handle the case of a non-directed receive, which is also referred to as any source, where one receive buffer can match to a message from any peer, local or remote. So to ensure both providers have access to all those buffers, and that we can maintain ordering of those posted buffers, we need to import access to the entire receive context for use with all the providers. And then finally, we need to share addressing information across the peers to make sure that all providers agree to the same addressing to report back to the application when needed, or to use in communication with each other. So we all need to agree that peer X is FI adder 3 and that peer Y is FI adder 1. So when we talk about the peer API as a whole, what we're referring to is the set of APIs that allow for sharing this information across providers. So if a provider says that it supports the peer API, it means that it can be used as a peer through these APIs. And not all providers implement these features. One of my goals here today and in general is just to spread information about the peer API for both app developers and provider developers, so people can know whether using a peer provider model is right for them, and whether there is interest for a provider to support this model. So if you see this presentation and you're thinking, dang, I wish provider X could do this with shared memory, that would be super useful to me, well, reach out on GitHub and let's get a conversation going, because right now, we only have a few. The shared memory provider supports this, obviously. And then for remote providers, we have CXI for Cassini Slingshot, which supports it, as well as RxM, which makes it usable for verbs and TCP. The AWS EFA provider doesn't support this through LNX yet, but it does use shared memory internally through the peer API to offload communication. And so whether the provider goes through LNX or directly imports relevant peers internally is up to them. There are pros and cons to each of them. So here's an overview of those two setups that I was talking about. So on the left, we have what Amazon's EFA provider does today, where it acts as the owner of the shared resource and then imports those resources into shared memory, basically telling the shared memory provider not to use its own completion queue and receive context, but to use the imported resources through those peer API calls. So when the app posts a send, the EFA provider finds out whether it's for an internal or external peer, and then we'll send it either through the EFA provider resources, or we'll just pass it through to the shared memory provider instance. So when the send is done, the shared memory provider can report the completion directly to the app CQ. So after the EFA posts that send to SHMEM, EFA can basically consider the transfer completely in SHMEM's hands, and it doesn't have to process the message anymore. On the right, we have the LNX setup, where LNX is acting as the owner of all these resources, so the CQ and the context. So it'll open up an instance of an internode provider. In this example, I just use RxM for remote communication, and then an instance of the shared memory provider for local communication. And then it will import the resources into both RxM and SHMEM, directing all communication requests that it gets into one of those two providers. Similar to the EFA setup on the left, once that message is redirected to the appropriate provider, LNX doesn't have to manage that transfer anymore, as it's completely in RxM or SHMEM's hands. And once the transfer is done, the provider who sent the message will just write a completion directly into the application CQ, which will be available on the next CQ read call. So LNX doesn't have to intercept and copy that completion over anywhere from one provider to the app CQ. There's not a fixed rule on what a provider needs to do to support shared memory offload. It doesn't necessarily have to be used as a peer like EFA on the left. If it wants to go through LNX and not have to worry about managing those peer resources and directing traffic, so basically trying to fit into the setup on the right, then it has to be able to be used as a peer. So all those light blue boxes in these diagrams are providers that are being used as a peer. So basically, they are not the owner of the resource and are agnostically going through these API calls, not really knowing what the resource itself looks like. If the provider is okay managing those resources, or maybe it has some optimizations it can use, or maybe some difficulty implementing the full peer API, it could be beneficial to go directly through SHMEM and then be its own owner. So there's no right answer on what's best for a provider to do. Both of these setups are completely valid and are being actively used today in Libfabric. Here's a closer look at those resources. So you can see EFA space here in the green, and then SHMEM here is in the purple. EFA owns those shared resources, and SHMEM is merely pointing to those EFA resources. So all the application calls are going through EFA. So if a receive is getting posted, it posts the buffer to the shared receive context. And that'll make it accessible to the shared memory provider whenever it receives a message and then needs a buffer to put it in, it'll query the shared receive context. On a send call, EFA looks at that addressing information for the target peers, and then we'll decide if the peer for this message is remote or local. And so if it's local, it can just pass it through to the shared memory provider. And so what that means also is that when inserting addresses into the shared memory AV, EFA has to use this flag called FIAV user ID, which allows SHMEM to know what the EFA FI adder is for both reporting to the CQ and then also for querying the shared receive context. So it's that agreement of addressing that I was talking about earlier. And then when SHMEM send is done, it can just write the completion directly to the app CQ. So like I said, on that next CQ read call, the SHMEM completion entry is available directly to the application. EFA doesn't have to copy that entry from the SHMEM CQ back to the application one. It's just ready to go. The LNX example looks a little bit more complicated, but it's essentially the exact same thing, just happening with two different providers. So LNX is going to own the shared resource in the blue up there, and then it'll just import that resource into both provider space. So again, in this example, RxM and SHMEM, but it doesn't have to be. LNX here isn't doing any communication itself, unlike EFA. It's just basically passing all of the messages through to one of the providers that it's using. And those providers will be using the shared resources that LNX manages. So LNX here is the entry point for the application for all calls. So all app calls like FI send, FI receive, FI CQ read, all of them are going to go through LNX, but they'll either be just passing through to a core provider case for like FI send, or they'll be reading a shared resource like CQ read, or they'll be writing to a shared resource like the FI receive, which will be inserting an entry into the shared receive context. So again, it looks more complicated than the EFA case, but it's essentially the same thing. It's just in these diagrams, I'm only showing the stuff that's relevant to the peer architecture. And in the EFA case, the same remote process is all happening. It's just happening outside of the scope of the peer API. And it's all happening inside the EFA box, which I'm not showing. And so EFA knows what it's writing to and can access the resource directly in a different way than SHMEM is accessing. But the whole flow of where the messages go is essentially the same. If you wanted to, you could replace the RxM box with the EFA if it supported that, and it would be the same. So we wanted to just do a quick demonstration of what this looks like in reality using a TCP example. With a provider like TCP that maybe doesn't have that optimized of local performance and is also prone to resource bottlenecking on the network, it could be useful to offload the local communication to shared memory. As I mentioned, RxM, which can be used with the TCP provider, it implements the peer API, so it can be used as a peer under LNX. So the two lines here are TCP alone in the blue, and then LNX, which is redirecting communication, either local communication through SHMEM or remote communication to TCP RxM in the orange. And this is only one run, and it's TCP, which has a lot of discrepancies, network issues. So take these little differences lightly, especially on the left where we're going through the network. But you can see that when we layer LNX on top of TCP using SHMEM, we maintain the same internode performance since LNX is just passing the sends directly through to TCP again. But on the right, If we look at local communication, LNX is now redirecting the communication through the instance of the shared memory provider. So we can achieve much higher bandwidth than what we could by going just through TCP using loopback. Not only is our performance better for local communication, but we're actually also clearing up space in TCP for more remote traffic. So it helps in other ways as well. Once again, this is just a two-process bandwidth test, so take it with a grain of salt. It's just one of our fab tests, a tag bandwidth test, two-sided. But we have validated LNX with MPI on a much larger scale, thousands of ranks. So it is all working, but this is just a simple demo. All of this data was gathered using the same application and executable. That's one of our fab tests, but just different runtime parameters. So it didn't require any app changes. So if your app only requires capabilities that LNX supports, then you could do this today. So I will show you how. So using LNX is just as simple as switching your provider to be LNX and then telling LNX which providers you want to link together. Right now, this is happening with environment variables. I don't love using environment variables for reasons that I'm not going to get into today. LNX is still really early on in its development. We're constantly modifying the setup and its capabilities, so it might change. But for now, environment variables are a really easy way to allow applications to leverage the support without requiring any app updates. So that's what we have for now, but it might change depending on how I feel that day. LNX currently only supports the tagged API, but the addition of message and RMA APIs are coming up next, so stay tuned. The reason behind starting with the tagged API is because that's what the OpenMPI OFI implementation requires, so it's a good starting point for scaled validation and tuning. So if you're using OpenMPI right now and want to target TCP verbs or CXI, your application should be just ready to go today with LNX. So I'm going to switch gears and pull up my little demo. And yeah, Raj, yell at me if you can't see this. So what I have set up is just, I pulled up two different instances of just a remote setup and local setup so we can do a side-by-side example of what this looks like. So we'll start with the remote example. So here I have my servers on the top are going to be on the system ICX4, and then I'm going to have some clients ICX5 remotely. So just to give us a starting off point, I have all these commands. So the first one is we're just going to start our server. We're going to just run TCP raw. So this is not LNX, it's just giving our baseline. So I tell TCP which interface to use because I happen to have multiple interfaces on the system. And I'm going to say which provider to use. So this is just a fab test argument, -p, which tells it which provider to select. Most applications that use OFI have a similar filtering where you set that. So here I'm just going to tell it I'm going to use TCP RXM, and I want it to go through the TCP interface ETH4. So now my server should be listening. So let me grab my client. So what we expect here is, regular TCP performance remote. It's not going to be great. It's TCP. I'm using a 1 gig Ethernet. It's, nothing special. So you can see we're heading up to, let's see where we max out. 1120 megabytes. That's where we are. So again, nothing crazy. Let's run it on LNX. So when we install LNX, what we're going to be doing is we're going to switch that provider now to -p LNX. So we're switching the provider that we're using to LNX, but we're telling LNX which providers we want to be linking together. So we say use SHMEM if possible. If not, use TCP RXM over this interface. So now I have my server running with LNX. What we should see here is pretty comparable performance. And that's because LNX notices that it is a remote address that you're talking to. And so it's not going to do anything different. It's just going to pass it directly through TCP. So let's see that. All right. Yeah, 60/60, same bandwidth. Let's see where we max out to make sure that we even out at the peak bandwidth at 8 megs. 1120, great. So exact same performance. It is literally just passing it through to TCP. nothing different is happening. So let's switch over to a local setup. So now I have my server still on ICX4, but now my client is also on ICX4. So let's see how TCP performs without LNX. So again, telling it that I'm using TCP ARXM and setting the Ethernet. Let's see how our local performance does. Okay, definitely better than our remote communication. We're maxing at about 10, 11 gigs here. There's probably cache line differences there that drops. So, this is what we'd expect with loopback. So let's see if LNX can do anything better for us. So again, LNX is the provider, telling it which providers to link together. So what we expect here is for LNX to notice that this is actually on the same system. Let me just send it right through to the shared memory implementation. Let's see what happens. Nice. We drop our latency significantly. Our peak bandwidth now getting to 29 gigs. Amazing. Again, drop for cache line. So this is the potential that LNX has for you. Is it'll just do that recognition on the fly. You don't have to do anything. You don't have to have your own shared memory implementation. You are just ready to go. And that's the goal of LNX. I'm going to switch back to the slides. So you can see our goal here is just to make as many tools available for users and make them as simple as possible without requiring everyone to change their applications. This is going to be really important as we move into the UEC space, because we're going to start seeing an increase in users, an increase in providers, and the more solutions that we have ready to go, the more those users and providers can just plug and play with these common solutions. And that helps the development and maintenance time for everyone. So now Raj is going to give an overview of UEC, what it is, and how Libfabric will fit into that landscape.
Thank you, Alexia. So this slide shows the comparison between the legacy RDMA and the UEC transport. So RDMA is good, but it also lacks few things, especially for the requirements of modern AI needs. With RDMA, multipathing is at flow level, meaning it manages entire stream of data and can manage congestion by rerouting the entire flow based on the feedback from the network. It has DCQCN, which is congestion control mechanism that aims to manage network congestions effectively. And it also relies on ECN, which is explicit congestion notification, wherein it detects the congestion early on and it provides the feedback to the sender and can adjust the transmission rates to maintain the optimal network performance. But all of this is a little bit brittle and it is hard to tune. And it requires careful manual tuning for performance, and its tuning is also sensitive to latency, speed, and buffering capabilities of network that's beneath it. And it requires in-order packet delivery, and the security is not really addressed. And it scales to a few thousand nodes, wherein the AI needs are like, to scale at a higher uh, connections of like at least 1 million Q pairs there. So what is involved with UET stack? The UET is Ultra Ethernet stack. So UET is focused on enabling HPC and AI use cases. It targets to provide the highly optimized services for carrying out RDMA in AI and HPC workloads. We have seen yesterday, Torsten gave an exclusive talk on the Ultra Ethernet itself. So it is like he mentioned also, it is targeting to cater hyperscale computing and AI with at least 1 million simultaneous endpoints. The diagram on the right shows the layers of the UET. So we can see the physical layer at the bottom, link layer, network layer, transport, and software. In the software layer, we see that middleware libraries are there that are stacked on the Libfabric. So Libfabric is chosen as an API abstraction for Ultra Ethernet transport as well. So like we have shown in the initial slides that in the provider set, we will eventually have one UET provider as well. So Libfabric interfaces with the transport layer where the semantics and packet delivery stuff is there, which is mostly in the transport layer there that is shown in the blue boxes there. So Libfabric will have to interface into that layer and then deal with anything that is mapping there. So many of the features of UET will help us help achieve this with the features which are present in the semantic layers, or the features that are present in the packet delivery layers, or the things that are handled as part of congestion management. So the semantic layer, the SES layer, is designed to integrate into broadly deployed AI frameworks and HPC libraries through the Libfabric mapping. This layer specifies a protocol that defines how application messages are identified, how the associated buffers are addressed, how the preferred operations on the messages are actually deployed. So it is the interface between the Libfabric and the transport. The PDS, it implements reliable transmission for the SES, for like out of order packet delivery, and the concurrency in the network and application is maximized, and the latency is minimized. With the efficient rate control algorithms that are there in the PDS, it allows the transport to quickly ramp to the wire rate while not causing the performance loss for any competing flows. And this PDS layer also defines a protocol with multiple modes of operation that offer all combinations of reliable, unreliable, ordered, and unordered packet delivery services. Next, there is also like a congestion management sublayer within the transport. Uh, this deals with like it helps with like high network efficiency, and it reduces the latencies. And these are achieved by enabling multipath packet spraying across the fabric, and like avoiding the hotspots when congestion signal arrives. Then there are like traffic classes that are used in the network to separate different traffic flows that have different characteristics and the requirements from the network. And end-to-end telemetry will help us signal the congestion ahead of time. So and then there is also a security sublayer that is considered as a first-class citizen, and security is built in as compared to the RDMA stack we've seen before. So these are just like, quick touch points on the different features within the UVC stack, with Ultra Ethernet transport stack, that will have the mapping in the Libfabric layer also. So let's see what are the changes in the Libfabric to map to the UET. This diagram shows the software layers with the focus on the Libfabric and how the UET provider is fitting in. Basically, the goal is to extend and change the Libfabric to support the Ultra Ethernet profiles. And in the previous slide, we discussed like some of the key features of UET as well. So here, the application on the top will not have to make any changes, and so for it to use UET transport. With the same Libfabric APIs and along with the appropriate parameters and flags, it can just work. So let's see how the transport features are being mapped into Libfabric's like major components, like the control, communication, completion, and data transfers. Let's do the control first. So in the control, we have discovery APIs in Libfabric, like FI get info, and there the Libfabric version should be like at least 2.0 or greater than that. So because all the features, any support for UET is provided from that version onwards. And in the get info also, we have some predefined services like CCL, MPI, SHMEM that are required for the UET transport as well. Next, the communication. This is where it deals with the fabric endpoints. A new value FI ADDR UET is added to the enumeration in the Libfabric library to identify Ultra Ethernet transport address formats. The address format is a little bit different. So FI ADDR UET will recognize that this is a UET type of address format. And UET endpoint addresses include bits for like Fabric endpoint capabilities that will specify different AI, different profiles that UET is supporting. So UET supports profiles like AI full, AI basic, and HPC. So the endpoints in the Libfabric will have bits that will specify like which are the UET profiles that are available or like that we can specify. And then there are like various flags that are aligning with the UET to indicate the validity of PID on FAP, basically the process ID for the Fabric endpoint. Then to indicate the relative or absolute addressing and other things like Fabric address, initiator ID, etc. So the Libfabric endpoint addresses, they are allocated when the UET endpoints are opened. So next we will see the completion and data transfer APIs. So this table shows the completion counter requirements for various UET profiles. So for AI full, we need the completion counters for FI send, FI receive, FI read, FI write. And similarly for the HPC profiles, these are the completion counters that are like required, that must be there. So for AI based, it specifies there are like none. It's not compulsory there. So the next table shows the APIs that must be supported for data transfers for different type of endpoints and for different type of data transfers. So for FI message, variations of FI send and FI receive APIs must be supported with both datagram endpoints and RDM endpoints. So UET providers also must support FI EP datagram and FI EP RDM endpoints. So and similarly, like for the other type of endpoints like RDM endpoints, and along with the different type of data transfers, we have listed the APIs that must be supported. Next, we'll see how packet delivery is handled. So Libfabric endpoints of type FI EP datagram, they must use UET's UUD packet delivery mode, which is like unreliable, unordered delivery. And then the RDM endpoints, they must support the ROD, RUD, and RUDY delivery modes. The ordering requested at the Libfabric layer that is passed to the SES layer of the UET stack so that it can select the packet delivery modes and how those packet delivery modes are being used. So basically, there are like different mappings of various structures within the Libfabric library itself that will have these different values that can be passed to the SES layer and ultimately to the transport for it to operate accordingly. Then there are like traffic classes. The SES sublayer is aware of only data traffic class. The Libfabric application actually is not aware of different traffic classes that are used by the packet delivery subsystem. There is one field called T class in the FI domain attribute. So whenever we create the domain resource, so there is a field called T class that will control, that will have the information about the data traffic class that is going to be used, whether it is going to use a default one or something else. Then job IDs, this is something additional. So a job is often started collectively and it is uniquely identified by a job ID within a cluster. And job IDs are used for addressing and authorizing purposes. The reason why we are mentioning job IDs here is there is a flow. A privileged entity will provide the assigned job IDs to the provider's kernel driver, and that gets passed to the Libfabric. And whenever the Libfabric is passing that job ID to the underlying UET provider, then that must be validated in the hardware context. And that is why we we are talking about the job ID here, because that is also another thing that kind of flows from Libfabric as well. So there are some other parts of Ultra Ethernet Libfabric mapping that we are not covering here. There is a lot that's available in the 1.0 spec that is publicly available. I tried to touch on some little parts here, and the spec is really huge, and the mappings are specified in very detail over there, like which structures are to be modified, what functions are to be supported, and things like that. And UVC is also working on the next version of the spec to include many other things, and is also working on a reference provider there. So let's wrap up with what we have heard. So just to summarize, we discussed what's Libfabric, what are the different type of endpoints, what are the different type of data transfers, and we also saw some example snapshots. The examples were some examples were presented in the previous conference presentation, same HOTI conference presentations, and those will be posted on the Libfabric GitHub repository. And in the interest of time, we did not cover atomic and datagram endpoints. And we also saw utility provider briefly about the profile hook provider that was also presented, and the examples were also there. And we saw in detail the link provider. And we also saw some insights into the Libfabric UET Libfabric mapping as well. So we hope this was insightful.
Yeah, and below are just a few links for more information. The first one is just for our the main page of our GitHub developers manual. And then there are man pages for more detailed information on the API calls and other features. And if you're sitting here thinking, dang, this is interesting, but I wish they would go more into the APIs themselves. I don't know how to use Libfabric. How do I use it? How do I code to the API? Well, you're in luck. This was good timing because I'm giving a webinar next week on Wednesday where I'll be going more in depth on these APIs as an intro, talking about some of the nuances, the best practice tips, conventions. So if that sounds interesting to you, go to openfabrics.org to learn more and register. If you want to learn more about UEC and what they're trying to do over there, check out their webpage and their 1.0 specification, which was recently made public, and it contains a lot of detailed information about their Libfabric mapping. And so with that, thank you so much for attending our talk. We hope you learned something new. We'll be monitoring the Slack channel for any questions, and please feel free to engage with us on GitHub anytime you want for any future questions or bigger discussions. Thank you so much.
Yeah, thank you all. And
all right, thank you so much to the previous speakers. The next tutorial is going to be GPU communication libraries for accelerating HPC and AI applications. This will be about a comprehensive introduction to two advanced GPU communication libraries, Nickel and NVSHMEM. Our presenters are Benjamin Glick, who is a senior software engineer at NVIDIA, specializing in GPU communication libraries, high-performance computing, and scalable system software. He currently focuses on NVSHMEM, making high-performance, GPU-aware distributed programming more accessible to developers. Prior to NVIDIA, Ben held engineering roles at AI hardware startups, including Sapion and Samba Nova Systems, where he designed distributed operating systems, memory and I/O architectures, collective communication libraries, and virtualization frameworks for custom AI accelerators. He's led software and hardware co-design efforts spanning multiple product generations, from pre-silicon through deployment. Ben's expertise includes parallel and distributed runtime systems, accelerator and OS architecture, GPU and network optimized communication, and HPC AI infrastructure. His work has been published at SC and Ross and deployed in advanced AI and HPC environments worldwide. Arnav Goel is a senior systems software engineer at NVIDIA Corporation. Specializing in GPU communications, reconfigurable data flow architectures, and high-performance networking, he earned an MS in electrical engineering from the University of Southern California and a Bachelor's of Engineering in Electrical and Electronics in BITS Pilani, India. He possesses over 8 years of industry experience encompassing enterprise-grade data center networking systems, including Cisco Nexus ACI, Oracle X5 Server, AI, ML compiler frameworks, and distributed training libraries such as PyTorch, XLA, Torch Distributed. His technical expertise includes developing communication libraries using user space networking stacks, RDMA verbs, DPDK, ETHDEV, and system software runtimes for AI accelerators, such as Samba Nova's RDU, and modern NVIDIA GPUs. He has authored multiple publications in VLSI design and SC ROS, and holds 15 more patents in reconfigurable data flow architecture, particularly reconfigurable processor as a service systems, network acceleration, and runtime virtualization frameworks. Currently, he advances GPU communication libraries, including NVIDIA's NCCL and NVSHMEM, with a continued focus on hardware, software, co-design methodologies for next-generation AI and HPC communication architectures. Andreas Herten is a researcher at Jülich Supercomputing Center, heading the Accelerator Devices Lab within the Novel System Architecture Design Division, where he co-leads. He is a lecturer at the University of Cologne. He is part of the NVIDIA Application Lab, in which he analyzes, ports, and optimizes scientific applications for GPUs. He is part of the core Jupyter team to deploy the system. Andreas is also involved in a number of EU-funded projects for improving scalability of accelerated applications and libraries. And finally, we have Puya Kusha, who's a senior HPC software developer at NVIDIA, specializing in optimizing HPC communication and performance analysis at scale. His work spans benchmarking and AI workloads to ensure efficient data transfer in large-scale HPC environments. During his PhD at The Ohio State University, he focused on advancing HPC communication through runtime libraries like MVAPICH2 and profiling tools such as OSU Enum. His research centered on designing real-time, scalable profiling tools to identify and resolve communication bottlenecks critical for system performance. He also integrated conversational AI interfaces to enhance HPC user task execution. Dr. Kusha has led multiple software releases of OSU Enum and contributed to MVAPICH2, which are widely deployed at HPC centers worldwide. His expertise includes performance analysis, parallel programming, high-performance deep learning, and HPC architecture. And I'll let them take it away. Thank you so much.
Thank you, Jackson, for that lovely introduction. Hi, my name is Arnav. Myself, Ben, and Puya will be giving this tutorial today. I would like to welcome you guys to the Day 3 Track 2 of the IEEE Hot Interconnects. Myself, Puya, and Ben are from the GPU Communications and Networking Group at NVIDIA, and Andreas from the Jülich Supercomputer would be presenting a tutorial on GPU communication libraries for accelerating HPC and AI applications. This talk will help you provide a comprehensive introduction to two of the most premier GPU-centric communication libraries at NVIDIA, NVIDIA Collective Communication Libraries NCCL, and NVIDIA's OpenSHMEM implementation, NVSHMEM. Before I begin the talk, I would like to give the opportunity to Andreas to provide us a brief introduction to the Jülich Supercomputer. Over to you, Andreas.
Thank you, Arnav. Let me just quickly start my screen share with the slides. All right, so they should be visible now. So hi, also from me, Jackson, thank you for the introduction. I'm indeed from Jülich. It's a town in Germany. Hard to pronounce for outsiders. We have these umlauts. We are not making it easy. But we are actually quite a large facility. So our computing center is called Munich Supercomputing Center, and we are embedded in the Forschungszentrum Munich, which is a multidisciplinary research center near Cologne, so in the west of Germany, with around 7,500 employees. And my institute is working on operation of supercomputers, educating and training people, supporting on a technical and domain science level, and trying to research and develop the next generation of supercomputers. We are doing this with around 360 employees. And yeah, as mentioned before, I'm the joint head of a division called Novel System Architecture Design, where we are looking forward in the future, finding out what works well, what doesn't work so well. And yeah, our specialty at the moment is, of course, GPUs, which is the enabler of the exascale era, and it kept us busy the last years, but we have great results, which we are also using today. So we have a different kind of supercomputers. Jupiter, Joules, or Eureka are the names, and we are quite proud on the Jupiter system, which I'm going to tell you a little bit about right now. So on the lower right side, you see a bird's eye view of our campus. It's in the middle of a green forest area, quite nice. And if you zoom in here at the very upper part here, you're going to see our building, where right here on the lower side now, the Jupyter data center is being assembled. So as we speak, because the system is not ready yet, but you can still go inside and, oh, sorry, one too many, and see how the racks come together and how the whole system is being built up. So Jupyter is a supercomputer with 2 modules. We are currently deploying the Jupyter Booster module, which is an exascale system. So on the high-performance NIMPAC, we clock in beyond 1 exaflop of performance. And we're doing this by using 6,000 nodes, each with 4 Grace Hopper superchips inside and 4 times NDR 200 network. There will also be a Jupyter cluster, which is more focusing on ARM CPUs, but we're not deploying this yet. Network is also from NVIDIA, like the Grace Hopper superchip, and we are also having nearly 1 exabyte of storage on the system, doing this all in a very tight energy envelope of around 17 megawatts when we run the HPL. And it's a very efficient system, and we are quite happy to have this. And one specialty is that we are deploying this in a modular data center of containers. So maybe you saw this in the bird's eye picture. Everything is like Lego bricks. You can stack them together and expand and scale out the system. But we've bought this now in a fixed amount, and the node topology is looking like this. So we have 4 CPUs, 4 GPUs, and attached are 4 network adapters. If you zoom in a little bit, this is the view you get, and here you, for instance, see the 72 cores of each of the gray CPUs, which give us a lot of quite energy efficient performance on the system, and then of course the Hopper GPUs. We were hoping to give you access to Jupyter today, but unfortunately the system is still being commissioned and finished. So today we're using the predecessor of the system, and that is Joules Booster, but you're going to see it's very similar. So it's a system which we're operating already since 5 years, and it is our stepping stone towards the exascale era, not featuring 6,000 nodes, but roughly 1,000 nodes with AMD CPUs. There was no Grace at the time. Well, no Grace CPU at the time, of course there was Grace. Each node features 4 A100 GPUs with 40 gigabytes memory, and it's interconnected by an InfiniBand HDR200 network, giving you 400 gigabits per second per node in Dragonfly topology. And it was quite a fast system when it came out in November 2020, and it's still one of the fastest systems in Europe. Topology-wise, it's looking very similar to what you've seen before. So we have the GPUs all-to-all connected, which is also good for nickel and NVSHMEM workloads. So this is why I make a point out of this. And every GPU gets its own network adapter, so that there is really a good bandwidth which you can get from one GPU to the GPU of another node. The network is a Dragonfly Plus network where there is a difference between a global topology and a local topology. So we assemble groups of nodes together in sets of 48 nodes, and then they are connected by switches in 2 levels. So there is a full-fed tree in those 2 levels, and I put down here all the details in case you find this interesting. But we have a strided connection so that the network adapters of subsequent nodes are really on the same switch. And with this, you have a few hops between one node and another node. And Nickel works very well with this because, of course, Nickel allows you then to use inside node topology to shortcut these ways and make good performance for your multi-node workloads. Then zooming out of the node, these are the northbound links here. We have a somewhat more sparse connectivity where we connect 20 groups together, each with 10 links, so that there is still some performance available, and this is done via adaptive routing. So this is the system we are going to use today. Those of you who found this topic already interesting in the last weeks and signed up for hot interconnects, we asked you to onboard in advance because we are Jülich and the Joule supercomputer is a public infrastructure, and we need to ensure some security measures in order to onboard people, and all of this just takes a little while. So we sent out frequent emails in the last week in order for you to sign up in time for this tutorial. The access was first you needed to register for the hot interconnects conference. Then we sent out invitations so that you can also register for the for a more local event management system called Indico. And when you did this, I clarified this then with the hot interconnects people. We sent out registrations in order to access our UDOR ecosystem, where you can request accounts for our supercomputers. And when you did this, I asked you to log in through our Jupyter infrastructure and launch a terminal on Jupyter, this time with a Y, Jupyter. And I asked everyone to send back a magical constant after source in the course environment. So I ask now you who are here and have done all these steps to please start a fresh terminal, start in Jupyter and source the training environment. So this is super important because we have basically hidden a lot of environment variables and commands and other things in this environment. Also, the whole software dependency infrastructure is hidden in there. And then when you've done this, you will see a banner, like a message of the day, which greets you in this course. And when that is done, you can call the JSC material sync command here on the lower shell, which will sync our main repository into your home directory, so that you can find the material in the hot I-25 directory in your home directory. I'll flash the slide again in a second, but first I want to show you a few screenshots how this looks. So you access our Jupyter portal, you hit the sign in button, and then you are asked to provide UDOR credentials. So it's an OAuth process where UDOR then is the next step. So when you've done this, you can create a new Jupyter instance, which I pre-configured for you. It's important that this is launched on Joules, that you're using the proper training project, and that you're using the proper partition, which is the login node of our booster system. Then you can hit start on the upper right side. It usually takes a little, but then you should be greeted like this, which is the launcher pane of Jupyter. And then on the lower part here, you find the money and also the $sign of the terminal, which you please hit. And then you have your terminal in the browser, which is very convenient. And you are logged into the supercomputer now, and you can use exactly the command as before, and which you have done already by sending the magical constant. So source $project _ training 2537/env.sh. And then after you've done this, you will be greeted with this kind of banner where the last stuff which is printed is called the JSC material sync, which you please now enter and sync everything into your home directory in the folder called hot I. I'll put the slide here up again. I hope that everyone who is interested has done this. If not, message me on the Slack and I'll try to get you in, but I can make no promises that this works. So we consciously required everyone to do this before the tutorial because Arnav, Pooja, and Ben created a lot of content, and we didn't want to bore everyone with now collectively signing up to the supercomputer. You rather should learn something about nickel and vSHMEM, and I saw the material. It's pretty good. So rather, we wanted you to do this beforehand, but I'll stick around a little bit to try to help you onto the system still. But yeah, we hope you're not you're not angry with us if it doesn't work out. Anyway, I want to conclude now and don't steal any more time of the others. So we are using today infrastructure in Germany from the UD Supercomputing Center. We are deploying Jupyter right now, the first European exascale system. Yeah, it can be accessed at the moment, but not for tutorials like this. And we are instead using the predecessor system, JUICE Booster, which is still the fast system in Germany. And it's a blueprint for Jupyter for us. And yeah, we are set up everything for the following 3 hours to work smoothly. But please start a new shell in your Jupyter environment and source the course environment. All right. So message me on Slack if you have questions, and I now give over to Arnav, I would assume. Thank you.